welcome to this talk about the Revenge Next Generation Decompiler at Black Hat Arsenal 2025. I'm Pietro Fezzardi. Alessandro Di Federico is here with me today. We are the two main developers of this tool, and today we're going to talk about it. The talk is going to start with a brief introduction about what Revenge is and how you can install it on your machine, and then I'm going to do a demo on how you can use Revenge from the command line and interact with its outputs. And then Alessandro is going to show you how you can script Revenge with Python. So what is Revenge? Revenge is a binary analysis framework with an interactive decompiler and a graphical user interface. The decompiler focuses only on native code and is completely open source. It is based on modern open source technologies, namely the QEMU emulator and the LLVM compiler framework. It supports many different CPU architectures. In particular, thanks to QEMU, we can easily target all the inputs architecture that QEMU supports without too much of an effort. And that's the main reason why we use QEMU. LLVM instead allows us to tap into a wide library of program analysis and transformations. We will see more about it in a moment. So the Revenge decompiler internally is structured as follows. It starts from many different executable binaries, possibly for different instruction sets. We currently support ARM, Arch64, x86, x86-64, S390, which is the IBM mainframe architecture, and MIPS. Each of these input binaries can be lifted to QEMU Tinecode. QEMU Tinecode is an intermediate representation of the QEMU emulator, but we are not doing emulation. So we start from different binary formats, such as Mako, ELF, PECOF, or you can even import an IDB from IDA. And then we use QEMU as a library just for lifting the input binaries to an architecture-independent program representation. Okay. Now, the QEMU Tinecode is designed for QEMU, so for fast emulation, so runtime code generation. It's not designed for advanced analysis, which is something you have to do heavily when you are decompiling. So in order to do this kind of analysis, we translate the QEMU Tinecode to LLVM-IR. LLVM-IR is the intermediate representation of the LLVM compiler framework, a very mature compiler framework powering, for example, the clang C++ compiler or the Rust compiler or many others. So this intermediate representation is very different from QEMU in the sense that it's designed to perform powerful and advanced analysis and transformations, and that's exactly what we do. So we reuse many of the analyses and optimizations that come with LLVM, and we implement many of our own that are specific for the compilation until we progressively recover a high-level program representation that we can finally emit in C. And this is the decompiler, basically. The important thing to stress about this is that the C code emitted by the Revenge decompiler is always syntactically valid C99 code. This is not very common. Most decompilers actually generate pseudocode, not actual C code. Generating C code means that you can take that and feed it into any other analysis tool that works at the source level on C code, which is very valuable, and we're going to see a few examples in a moment. Now, let's start installing Revenge. You can do this following our documentation at docs.rev.ng. But the short story is that you can just curl the install script on your machine if you are on Linux or Windows subsystem for Linux. And this is going just to download a compressed tarball, including compile tools that you can put wherever you want on your machine and just rely on environment variable to work. If you are on macOS, this doesn't work out of the box. You have to use Docker. We provide Docker images for that. So once you have done that, you're ready, right? So I've done it beforehand for this presentation here. We are in an Arsenal directory. We have this Revenge directory here, which was decompressed by the installation script. And in here, we have all the binaries we use. Arsenal 0 and Arsenal 1 are a couple of directories that contains the demo that I'm going to show in a moment. Now, I'm going to export the path to the Revenge directory so that we can use the tools that are provided with it. Now, before starting with the actual demos, I want to stress that everything you're going to see from this point on is entirely available on GitHub at the Revenge demos repository. and it's only based on open source software, and you can reproduce it following the instructions I'm giving today, or with Docker. Now, let's start looking at what you can do on the command line with Revenge. Here we have a simple program, a linked list program. It's a stripped binary without debug symbols, and what I'm going to do now is to generate some decompiled C code from it. The way I can do this is with the revenge artifact command. This is the basic command that you can use from the command line to request artifacts from a binary to Revenge. There are many different artifacts. What's important for today is the emit recompilable archive artifact. This contains, so this is basically a compressed tarball again. It contains a directory with a C file containing all the decompiled code for the input binary, okay? So I'm gonna run revenge artifact now, asking for the emit recompilable archive artifact, passing the -- analyze flag, which instructs Revenge to run the initial auto-analysis on the input binary. And then, of course, I have to provide the input binary, which is the linked list binary now. So like I said, the output is a compressed tarball, so I'm piping it to tar xz so that I'm gonna obtain right here uncompressed directory with all the C files I need in there. Let's open this with VSCode. So this has generated a decompiled directory here with many C files in there. Let's open this with VSCode. Voila. So there's many files. The first is the attributes.h file. This contains a bunch of attributes that we use to decorate the C code we're going to see later. The helpers.h is not very interesting for today. Primitive types.h contains some type defs for primitive types we use. And then let's move on to more interesting things. The first is the types and globals.h file. This contains a lot of type definitions. All these types were entirely recovered from the binary during the compilation process by the Revenge decompiler, thanks to the -- analyze flag that we passed. Okay, there's many of them, and I want to stress that Revenge was capable of recovering these kind of things from the binary, even if the binary doesn't have the bug symbols and it was stripped. Now we're gonna get back to this in a moment. Let's go on with the real interesting part, which is the functions.c file. Okay, so this is the file. It contains, okay, let's fold all the functions so that we can look at one of them at a time. So there's many functions in here. All these functions have weird names, just including the address and the instruction set. This is because the binary doesn't have the bug symbol. Some of them have proper names. These are basically wrappers around dynamic library calls, because for dynamic libraries, for dynamic functions, we have names that are the symbol names. So Revenge can use those even if there are no debug symbols. So we have to figure out where the entry point of this program. I can do libc start main. Okay, so this is an invocation to the libc start main function. The libc start main is a function coming from the libc, of course, as the name suggests, and it's used to dispatch the execution of the program after startup to the main function. And the first argument is a function pointer pointing to main, so this function here must be the main. Let's go look at it. So here's the main. I'm gonna open the body. Let's rename this to main. The main is doing a few things. Let's go line by line. There's a couple of local variables that are integers, and then there's a local variable that is a pointer to a struct. And before going on, I want to look at this struct and see how it looks like. So this is the struct. So this is a type of this struct. The struct contains two fields. The first field is an array containing 5 64-bit integers. So the Revenge data layout analysis was capable of reasoning about all the program and about all the memory accesses in the program to figure out how the data is arranged in memory and infer types from that, and even array types like in this case. And not just array types like in this case, but also pointer types. So the second field of this struct is a pointer to struct 80 itself, okay? So looking at this, it seems to be a list node data structure, right? So it's a node of a linked list, and the pointer points to the next element in the list. So let's call this next, and let's call this, let's say, data. We don't know much about it yet. And then let's rename the struct to node t for better readability around. Okay, we can go back to functions.c, and as you can see, the renames were applied by VSCode because all this C code actually compiles. So all the language server protocols in VSCode work. So now we have this variable that is initialized with the return variables of this function call. Let's look at this function. This function is calling calloc 2 times. So it's allocating 2 things, and these things are 48 bits large. 48 bytes large, sorry. And if we go back and look at types and globals, you're gonna see that here, this struct is actually 48 bytes large because there's five integers of 64 bits and 1 pointer, which is on, this is an x86-64 binary. So it's basically 6 times 8 bytes, which is 48 bytes. So this is allocating 2 nodes basically, and then is setting the next field of the object pointed to by var1 to the address of var0. So it's initializing a list and allocating 2 nodes so that the next pointer of the first points to the second. So we can, I'm gonna go on and recall this and call this init list, let's say. So let's go back to its use, which is down here, and let's see what happens next. This is basically the head of the list, so we can call this head, and it's passed to another function that is probably doing something on the list. Let's go look at it. Inside this function, we have a loop, and the loop is using var0 as an indexion variable, and it's used to traverse the list through the next pointer. So we can call this, let's call it node ptr. Node ptr is initialized to the argument, and then at each iteration it is assigned to next until next is a null pointer, so until the end of the list, let's say. And then what the function does is iterates over all the elements in the list, and it assigns and it accumulates in var1 the result of this function call here. So this is basically the result, and this is, let's call this accumulate. Okay, now there is still this function left. Let's look at it. This takes again a pointer to a node, and it contains a loop as well. This loop has an induction variable which is var0, initialized to 0 and incremented by 1 at each loop iteration. Let's rename this to I because it's an induction variable. And what happens here is that var1 is initialized to 0, and at each iteration of the loop, it's incremented by the data at position I that we can find in the node pointed to by the argument. So this is basically summing all the data, sum data, okay? So this is pretty cool. This is the compiled C code. I can open it in VS Code and just play around with it as if it was regular C code, because it is, okay? And being capable of using C code generated by a decompiler so seamlessly enables more advanced scenarios, one of which I'm gonna show you now, okay? So whenever you're dealing with source code, the typical thing you can do is to use static analysis tools on the source code at the source level. And you can't typically do that on a binary. But given that rev.ng generates syntactically valid C code, it enables you to use tools that are meant to be used on the source on the binary, just on the decompiled code, okay? So I have another binary here, the use after free binary. And what I'm gonna do now is that I'm just going to decompile it and run some static analysis tools on it, okay? So again, same command as before, this time on the use after free binary. Again, this generates a directory here containing all the decompiled C code. And what I'm going to do now is to use clang static analyzer on it. Clang static analyzer is a source level static analysis tool that performs symbolic execution. It comes with the clang compiler and it supports C and C++. So I'm running it. This is actually a script that invokes this command. So it's clang with a bunch of other arguments to spawn up the clang static analyzer. And I get a bug report. It says there's a use after free in my program, okay? And let's look at it, okay? I told you that we can open this up in VSCode. We can still do this. Okay, I can open the decompiled directory here. So in this case, we have nice names because the binary has the bug symbols. And there's a main that is calling do stuff. We are looking for line 99. Let's see. Line 99 is in here. And as you can see, this do stuff function allocates 4 bytes. Okay. And then when the argument is larger than 4, it frees the memory that was allocated by this call to malloc. Then the execution falls through, and here var0 is dereferenced. So probably this was supposed to be an error condition, and the programmer forgot to return an error code from do stuff, so the execution falls through here. So this is C code generated from a binary with revenge, and static analysis tools can deal with it and provide you useful bug reports on the binary, even if you don't have the source code. Bonus points, clang static analyzer can generate HTML output. So this is what we did with this flag here. I can open it up in my browser and say, let's look at this report. Okay, it's a web page that you can navigate. It shows decompiled C code interleaved with error messages that can guide you through the execution to see what are the specific conditions that need to be verified in order for the bug to be triggered. So you start from do stuff, and you are in a call to do stuff. You are calling malloc. Malloc returns allocated memory. When argument is larger than 4, you take the true branch. You hit a call to myFree that frees the memory. The execution falls through here until you hit the use after free. That's it for me. Thank you for your attention, and I'm going to give the stage to Alessandro for telling you something about Python scripting with revenge.